Welcome. On behalf of the National Transit Institute, I thank you for participating in the Transit Capacity and Quality of Service Manual Station Capacity webinar. The National Transit Institute develops, promotes, and delivers training and education programs for the public transit industry in the United States. The webinar format today consists of a presentation followed by a question and answer session. Paul Rees, Principal Engineer with Kittleson and Associates and Principal Investigator for the third edition of the Transit Capacity and Quality of Service Manual, will be available to answer chat questions during the presentation. Questions can be submitted by using the chat pod that is located in the lower left-hand corner of your screen. We are pleased to have Mark Walker with us today. Mark Walker is a Principal Professional Associate and Senior Transportation Planner with Parsons Brinckerhoff. Based in PB's New York office for more than 27 years, Mark has been involved in numerous transit facility planning and design studies across the US and internationally. Mark has leading expertise in the design of transit stations and analysis of pedestrian flows in a variety of high-volume settings. In recent years, Mark has applied leading-edge pedestrian simulation software in numerous applications, along with traditional methods of passenger flow analysis. Mark was the lead author of the chapter on stations in both the second and third editions of the Transit Capacity and Quality of Service Manual. Now I will turn the presentation over to Mark.
Thank you, Michael. Our presentation today concerns the station capacity chapter of the Transit Capacity Manual. I'm going to go through an overview of the presentation, and then we'll go through some PowerPoint slides, and I have a bit of video to show as well from some simulation. So we're going to begin by talking a bit about the learning objectives for today's presentation. We'll give an overview of station types and the range of configurations, which are discussed in the Transit Capacity Quality of Service Manual. We'll talk about passenger circulation and level of service and how to analyze those. We'll talk about station elements and the capacity of those elements, how to analyze those. And finally, we'll discuss some example problems, and I'll show you a bit of the videos from some microsimulations of passenger flows. First, our learning objectives today are that you gain some understanding of the different types of transit stations, that you gain some familiarity with passenger circulation and level of service concepts, to learn about the range of station elements and the methods of measuring their capacities, and finally to consider some typical station analysis problems. And all of this relates both to actual application of these concepts, but also to give you a heads up on the contents of the Transit Capacity Manual, where you'll find much more detail about these issues and methods. First, there are some changes in the third edition of the manual, just released at the end of October, compared to the second edition. We have significantly expanded the discussion of passenger flow microsimulation in the discussion, as that field has developed significantly since the release of the first and second editions of the manual. We have introduced an alternate stair capacity method, which is based on stair lanes instead of the traditional stair width. Both of these are found in the original work by John Fruin, but the emphasis over the years has been on stair width, and the stair lanes method is also useful. We've added an introduction of a clearance time analysis method, which I'll explain a little bit more later. We've expanded the discussion of volume to capacity ratio analysis in addition to level service analysis, and there have been various updates throughout the chapter to the text and some of the graphics. First, to begin talking about station types and configurations. Transit stations come in a wide variety of sizes, configurations, purposes, from relatively small bus stops that are located on street, may have few or no amenities, transit centers that are typically located off street, sometimes integrated with on-street stops and off-street stops. And these may have very few amenities or they may be very elaborate, up to larger transit stations that are normally off-street, typically have many amenities, and can serve all the different modes and can be, of course, multimodal. That's ultimately the purpose of a station, is to connect modes, or at least pedestrians with each mode. Here are some examples of just some of the range of types of transit stations, all of which are discussed in the transit capacity manual. From a simple bus stop in the upper left corner in Albuquerque, an off-street transit center in San Diego, rapid transit BART station in San Francisco, and to a very large-scale Grand Central Terminal in New York and similar facilities to that. Now I'll talk a bit about passenger circulation and level service. As say, there's quite a bit more detail and information to be found in the manual. So I encourage you to pick up the manual and take a look inside it if you haven't already. First, pedestrian speed is related to pedestrian density. The more pedestrians are present in a space, the slower the average pedestrian speed. This seems rather obvious. People interact, and slower people impede the flow of those behind them. The ease of walking is diminished as things get more crowded. Flow, that is how many pedestrians can pass a given point, is a product of a simple formula of pedestrian speed and density. The volume equals the speed times the density. So the units there are pedestrians per foot per minute, or the equivalent in metric units. Average speed per pedestrian is related to both speed and flow by the formula given, where density is equal to speed and divided by volume. Most design problems in transit stations relate to solving for either a specific station element width, how wide should a stairway be, how wide should a corridor be, a platform if you're thinking of the volume walking down it, or a station element area, the platform area in terms of how many people will need to be waiting on it, entering and exiting, or other parts of a station, say a waiting area, how large do those need to be in square feet or square meters. The result is a station element that is sized to accommodate a given number of pedestrians per hour at a design level of service. The idea there is that in some facilities you'll accept, at least for a brief period of time, a more dense condition, a lower level of service. In other facilities you want to maintain a higher level of service, and the calculations will show you the correct dimensions and size of the elements to achieve either of those objectives. Other questions may include how many bus bays or loading areas are needed in a transit facility. Is there enough room for pedestrians to wait and circulate in the station? Is there enough space and passenger demand for particular amenities? Perhaps you're planning a facility that doesn't yet exist, and you're looking at both at forecast volumes and the required dimensions to achieve particular objectives, and ultimately also cost issues of what elements are justified based on the number of passengers and the demand for those elements. Additional design questions are passenger processing elements, that is stairs, escalators, fare gates, adequately sized and provided in sufficient number. That may be pretty obvious in an existing station. You'll see congestion if there is not a sufficient number. But the question, either in designing a new facility or in considering an expansion of an existing facility, is how many additional elements and what are the dimensions are required to accommodate a certain level of service and a certain expected passenger flow. Looking at the question a different way, which station elements are constraining capacity? If you have people passing along a sequence of taking an escalator, then passing through a fare control area, then perhaps another corridor or escalator, it may be that just one of those in particular is constraining capacity. The others may provide free flow if the one element that is constraining the situation were enlarged or the number of elements were increased. And finally, what are the requirements for emergency evacuation? Emergency evacuation, which we'll talk about in a little more detail, is an increasingly important element in station design, and there are specific requirements to be met in that regard. The Americans with Disabilities Act sets specific requirements that need to be met in the design of transit facilities. This applies to all new transit facilities in the United States and also to significant retrofits of existing facilities. These requirements are addressed in the Transit Capacity Quality of Service Manual to the extent that it impacts the sizing of station elements. Additional detail on this is available in documentation specifically related to the ADA compliance and meeting the objectives of that law. Transit Capacity Manual also provides input into the design process, but it isn't really a design manual. Now to talk a bit more detail on emergency evacuation of transit stations. A station design must address evacuation requirements. In particular, we focus on the NFPA 130 standard for evacuation of a transit station. And that code or guidance provides a maximum time both to evacuate platforms and a time to reach a point of safety. Those are currently set at 4 minutes to evacuate platforms and 6 minutes to reach a point of safety. And these are based on a reasonable worst case set of passenger accumulations, including some delay in service, looking at the travel time for the person most distant from the exit points, for instance, and some other factors that are specified in the NFPA 130 guidance. Overall passenger flow through a station is an important consideration. That is, you want to watch for bottlenecks that would impede the flow overall. And as I said before, the guidance for this is based on NFPA 130, which is referred to as the standard for fixed guideway transit and passenger rail systems. I think it's worth pointing out that NFPA 130 is most directly applicable to transit stations. Applying it in rail passenger stations and some other settings, which is often done, requires some interpretation as the patterns of movement and accumulation of passengers in those facilities can differ quite a bit from transit stations, but the principles and ideas in there are really uniform across these kinds of facilities. Some additional detail on NFPA 130. Sufficient exit capacity to evacuate the station occupants, including those on trains, from platforms is required in 4 minutes or less. So this requires not only those people who would be normally accumulating on a platform waiting for an arriving train, and not only those who would normally be getting off the train at that station, but the entire train load has to be assumed to evacuate at each station, so that if there is a problem further down the line or in case the train is unable to move further, the entire load on the train is able to evacuate. Secondly, that sufficient exit capacity is required to get from the most remote point on the platform to a point of safety in 6 minutes or less. Fundamentally, a point of safety could be outside. Essentially, if it's an underground station, it could be reaching the street level. If it is an elevated platform station, likewise, it could be going down to the street. But there are also provisions in NFPA 130 to provide protected points that are secured from an incident that would happen on the platform on, say, a mezzanine, to designate that mezzanine as a point of safety by providing a suitable level of smoke and fire protection at that point. The NFPA 130 requires a second egress remote from the major egress route from each platform. So there can't just be one way off a platform. There could just be one public daily use entrance, but there has to be at least one additional either daily use entrance or an emergency exit stair that is positioned remote from that primary entrance. And there are also some specific additional requirements about the spacing relative to the ends of the platforms, for instance, for those exits. The maximum distance to any exit from a given point on the platform must not be more than 325 feet. Limits on assuming the availability for escalators during evacuation are included in NFPA 130. Essentially, the code requires that you assume that the escalator that would most adversely impact your evacuation is assumed to be not only out of service but unavailable, in the sense that typically when an escalator is undergoing service, the panels are removed so you can't even walk down it. The stairs may be removed or the panels at the end, so it is completely unavailable for exiting capacity. And NFPA 130 requires you to assume that just one escalator per route is out of service. And again, the above indications are based on the 2010 version of NFPA 130, and the elements included or referenced in the transit capacity manual were based on that. There is now a 2013 version of NFPA 130, which was released, I believe, earlier this month or last month. I think most of these fundamental elements are the same that we've discussed, but there are changes in some of the details. The loads of one peak period train on each track, continuing with some of the assumptions that go into the NFPA 130 analysis. If a platform has two tracks on alternate sides, then it must be assumed that a train has arrived in both directions, and that both of these plus the passenger load on the platform requires evacuation from the station. And finally, passengers on the platform during a peak 15-minute period must be evacuated, and there is the additional assumption that there is a delay. On the slide it says one headway late. The actual code has some interpretation about how to apply this consideration based on the operating plan of a system. It's critical that the maximum capacity required for both normal operations and emergency evacuation be considered, and that the larger of the two be considered in sizing each station element. Sometimes there tends to be a focus on the NFPA 130 analysis with the assumption that if you have fully satisfied it, the station should work okay during normal circumstances. That isn't always the case, or it may not be the case with a particular element within the station. Sometimes the maximum load would be applied during normal daily peak morning and evening operations, or during a special event type situation where a particular circulation element would carry a larger load than it would under the NFPA 130 criteria, or it would need to handle it faster than required in NFPA 130. As we noted earlier, NFPA 130 requires you to clear a platform in 4 minutes. Under normal daily circumstances, though, if you took 4 minutes to clear a platform, that would actually seem quite excessive. So normally you would be looking at a smaller number than that. Because emergency evacuation routes may be different than the routes taken by passengers during normal operations, don't assume that evacuation needs will govern in all cases. Essentially, a different way of saying what I was just talking about. Now we'll talk a bit about station elements and how the capacity of various elements is assessed. This figure is a station, I believe it's in western Portland, and it highlights examples in this one station of many of the types of items that we discuss: walkways, bus access that is outside the station. This is a light rail station on Portland's MAX system. Stairways, elevators, which serve not only the disabled, but passengers with carriages for children, people with larger luggage, those who simply prefer an elevator over stairs, or in some cases escalators, which are not found in this station. The platform itself, the guideway where the trains or a bus might operate, pedestrian access points, ticket machines, customer info. There's a kiosk here providing schedule information, benches and other amenities for the passengers, telephones. Lighting is critical, of course, to making stations not only safe but inviting in the evening and nighttime hours. And there were some additional elements that are often found at stations that were not shown in that particular image. Some of the key ones: restrooms. Some systems will provide them, some will not, based on policy. Bike storage, park and ride facilities. Some systems require fare gates. Portland's is a proof of payment system, so they don't use them. But fare gates are a key issue when figuring out the capacity and determining what elements are required when a system operates with that kind of fare arrangement, and some others that you can see here. Now to talk a bit about each of these elements and some of the methods of analyzing the capacity of them, starting with the waiting areas. A waiting area in a transit station is often the platform itself, but there can be other waiting areas as well with a station, depending on how complex and how large the station is. The process for sizing passenger waiting areas is based on designing for a desirable level of service. And as I said earlier, a typical design criterion is to design for level of service C during peak periods in a transit setting. Often level service B is desired in an intercity rail station setting, for instance. The concepts that this is based on were originally presented in John Fruin's book Pedestrian Planning and Design, which underwent a revision some years ago but has not been updated now in some time. But most of the key elements are presented either here in the Transit Capacity Quality Service Manual, or some of them for pedestrian sidewalks are taken in the Highway Capacity Manual. Also has a section which is partly based on John Fruin's work. It should be noted that the levels of service in the Transit Capacity Manual are intended for transit facilities, and there is a difference between the thresholds that are presented in the Highway Capacity Manual level service, which are for sidewalks. There is a bit of a difference in the perception of density in transit and sidewalks. This was reflected in Fruin's original work and is reflected. So you may compare two tables and you'll find out that they have slightly different criteria, and you should be using the correct one. So in a transit facility, the guidelines that are contained in the Transit Capacity Manual should be used, not those found in the Highway Capacity Manual. A level of service measure is essentially an average space per person. And here's an illustration of the Fruin concept of pedestrian level service. So you see that a level service A represents a very low density situation with more than 13 square feet per person. This provides very easy flow. People can essentially walk at the speed and direction that they desire with minimal interaction with other people. And at the bottom of the scale, level service F, where people have less than 2 square feet per person, is a very congested circumstance where movement really is restricted to sort of shuffling. You're likely at level service F and even at E to touch the shoulders of the people around you, to bump a little bit into other people at those densities. And the levels in between, as I said, a typical design standard is either level service C or the break point, it's called, between level service C and D. So it'd be the bottom range of level service C, which you can see here is 7 square feet per person in a waiting area. Now, in a walkway, the concepts are similar, but some of the measures are slightly different. These are some diagrams that are in the Transit Capacity Quality of Service Manual showing the relationship between pedestrian space and pedestrian flow rates. These again are adapted from Fruin's work, showing essentially a sweet spot of maximum pedestrian flow related to density and how pedestrian flow trails off as the density increases. A similar diagram to the one we were looking at just a moment ago about waiting areas. This now is for walking areas. I think I may have said that a little wrong when I first talked about it, but this one's specifically to walkways. Here again, level service A represents a very uncongested condition, making walking easy and comfortable. Level service F is highly congested. This is where movement is highly constrained and essentially rubbing shoulders with those around you. Another table, which is also taken directly from the Transit Capacity Manual, so you can find this reference there, which shows the square feet per person for each of the levels of service for walkways, and also shows some of the other factors, a volume capacity ratio, and there are actually a number of different ways to calculate volume capacity ratios. This is just one application using essentially absolute capacity, and some other measures of flow unit width versus the pedestrians per foot per minute, and typical flow speeds that were found by Fruin through observing circumstances under these various conditions. The typical average free flow pedestrian speed for design is 250 feet per minute. We recommend this for general design purposes. There are specific different rates that may be used. NFPA 130 has a specified rate that they use, which is slower to reflect that some people don't move at this average rate. And in some other cases, for instance, if you're working in a population that has a disproportionate number of the elderly, for instance, you might want to be using a lower average rate or perhaps be looking at the very lowest rates of the slowest walkers in the group, depending on what you're working on, what you're analyzing. Absolute capacity occurs at the breakpoint of level service E and F. That's where things essentially stop or nearly stop. Pedestrians move in a shuffle. On the other hand, we'll often specify a design capacity, which is level service either BC or CD. This gives an outline of a typical walkway design process in kind of straightforward order of based on a design level service, you identify the maximum flow rate per unit width that is desired. You estimate the demand for the peak 15-minute period or shorter periods in some cases. For instance, in transit systems, we'll often focus on the time period that represents the headway between transit vehicles or trains. Then allow for wheelchairs and people with large items, perhaps luggage, or if it's a circumstance where people might typically have other items that would take additional space or impede their flow. Then compute the design pedestrian flow, calculate the effective width, and these are all described in greater detail in the manual. And finally, provide an appropriate buffer to each side of a walkway. If there are walls, we typically provide a 1-foot buffer. Platform edges, there are various rules provided, both a safety buffer and then some additional, typically in the 18-inch range, but some locations may require a larger buffer than that for calculations, but people typically will allow about 18 inches to a platform edge. Lower obstructions, like a trash can, for instance, that's in a walkway, may impose a smaller buffer. About 6 inches is typical space people may leave between an object that's sort of lower than their shoulders or elbows in height. Now we'll talk a bit about the calculation of capacity for stairs and escalators. Again, showing a curve of the pedestrian flow on stairs, the relationship between the number of pedestrians per foot per minute and the space per pedestrian. Essentially, pedestrian flow quickly rises, then begins to fall off as density increases. And another way, another view of this movement relating the speed along the slope of a stair versus the space. And again, speed of movement increases pretty rapidly as the space per person increases, but it reaches a plateau at around 10 square feet per pedestrian, which corresponds to level service C. At that point, it essentially levels off. There's a slight growth as additional space is available, but it really reaches a plateau at about that point. Now a table again from Transit Capacity Manual showing the levels of service for stairways in both English units and metric units. I should also mention that all these tables that we've shown are available in the text. They're in English and sometimes metric, but there are additional tables there, I believe at the back of the manual. Paul can clarify that if I've got it wrong, that give all these in metric. So every one of the graphics, I believe, and the tables are also presented in the manual in metric for those working in those units. And so this, again, the descriptions here describe the kind of movement that you would expect, the sort of impedance that you would expect given these densities on stairways. A few things to consider when evaluating stairway capacity. First, even a minor reverse direction flow can significantly reduce stairway capacity. That's essentially because even if most people are going in one direction on a stair, a few people coming the other way essentially occupy a lane of that stair and restrict that flow, or as others pass them, they significantly slow down to work around the person coming in the opposite direction. So even though in percentage terms that counterflow might be quite small, a few percent, it can reduce the capacity of the stair by a much greater number. That also means that maximizing capacity of a stair, if you can achieve it, it would be maximized by having separate stairs for each direction. That's not usually provided in our systems, though. Although sizing procedures may suggest a continuum of stairway widths, the capacity is really added in one-person width increments of about 30 inches, 28 to 30 inches. We'll come back in a minute and then we talk about the stair lanes method, which is new to the third edition. Using the old method, if you add 1 or 2 inches to a stair, the old width method would give you an incremental increase in capacity, but in fact, a person can't really make much use of an additional 2 or 3 inches until you're adding something in the order of at least 24 inches and closer to 28 to 30 inches for full effect. You really haven't gained significant capacity. So this additional method looks at that alternate method of calculating stair capacity based on lanes rather than simply the width in inches or meters. Much new construction will use escalators as the primary vertical circulation element. We've seen this in a lot of new stations where there are an increasing number of escalators. On the other hand, cost considerations often restrict the application of escalators. And where stairs will be the primary circulation element, you typically would design those to level service CD. What the first one here is saying is that when escalators are the primary mode, you can design the stairs to a lower level of service on the basis they're not typically going to be used. They're really a fallback to the escalators. But in any case, the emergency evacuation needs may result in a better level of service during normal conditions than otherwise required. And now, similar to the previous design process for stairways, based on a desired level of service, you identify the maximum flow rate. estimate your peak 15-minute demand, compute the design pedestrian flow, and from that calculate the required width. And if there are minor reverse direction flows, then you would add the width typically of one pedestrian lane to the calculation. Again, there's additional discussion and explanation of this process in the manual. Now talking a bit about escalators themselves. Escalators typically in the US especially and internationally come in three sizes. There is single, intermediate, and double width. Typically those have a tread width of 24 inches for the single, 30 for the intermediate, and 40 for the double width escalators. And operating speeds vary somewhat. The most typical speed in transit systems has been 90 feet per minute. Some locations in the US use 120 feet, but that is often restricted by insurance considerations. Now an increasing number of systems are looking at an intermediate speed of 100 feet per minute, and that's measured along the diagonal of the escalator. And that increases the capacity a bit and moves people along a little faster. It should be noted that manufacturers often state a capacity for an escalator based on a theoretical capacity, as if you could put two people on every step of the escalator. In fact, this really never occurs in actual practice. The actual capacity obtained is closer to one person per step, or you could think of that as two people standing on every other step. Some places we've seen volumes a little bit higher than that, where some people will step on the next step and crowd in a little bit. But the capacity in reality is pretty close to counting the number of steps based on the speed of the escalator. Some of the factors that would reduce the effective capacity of escalators include pedestrians arriving in an intermittent pattern, for instance, after trains or buses arrive. If you do an analysis over 15 minutes, you might find that on average, the escalator is able to carry a certain number of people if they continually arrive at a certain pace, but in fact they may be arriving in these pulses after transit vehicles. So the pedestrians actually are experiencing then a level of congestion in that case, because there are other times when the escalator was being relatively unused, then it has a high demand. So in that case, it's important to look at the pattern of arrival of the passengers. Pedestrian hesitation at boarding escalators can have some effect on capacity. To some extent, when we go out in the real world and measure actual volumes, it of course includes a range of the people who are actually using our transit facilities. So to some extent, that would be included in data that you might gather locally about how many people will use an escalator. On the other hand, if you're designing a new facility where none exists, or especially if you're in an area where there is a particularly larger elderly population, for instance, this could become a bigger factor than it typically is. Likewise, pedestrians carrying baggage or packages, an escalator in an inner city train station or bus station, for instance, might experience a different capacity because the passengers there are more likely to be carrying baggage than, say, a daily commuting type setting. And finally, the pedestrian desire for comfortable spacing. People vary quite a bit in whether they will stand next to somebody they don't know on an escalator step, or especially if they would stand on the step directly before or in front of them. On the other hand, two or three people who know each other might stand quite close to each other on an escalator. Nominal capacity values based on one person for every other step, as I was indicating, are a good measure, working measure to work from in designing escalator capacity. And we found through analysis that intermediate width escalators typically have a capacity that is close to the capacity of a double width escalator. That may seem a little counterintuitive. Their width is exactly halfway between the width of a single width and a double width. You might think, therefore, that their capacity would be prorated equally. But what we find is that people will stand in a bit of a zigzag pattern on these intermediate stairs. Or escalators rather. It does tend to restrict walking on the escalator, but it allows people to stand on them in a density that is very nearly equal to the density we find on a double width escalator, and therefore the capacity is nearly equal, not quite equal. Now to talk a bit about elevators. Elevators are typically provided in a station to serve people with disabilities and to serve as an auxiliary to stairs and escalators. As I mentioned earlier, especially parents with children in strollers very often will use elevators. People with larger luggage that is inconvenient to move on a stair or an escalator might choose an elevator. And some people just choose them out of preference if they're available and the wait isn't too long. In some cases, though, they can be a primary vertical circulation method, especially in stations that are quite deep. We mentioned some examples here. New York has 3 such stations. Actually, there's a 4th one in Brooklyn. Washington, D.C. mentioned Forest Glen. There are others in Washington, I know, where quite a few of the people use the escalator or use the elevators because the escalator runs are quite long there. And in Portland, Oregon, the Washington Park station, which I believe the picture just before was from there. When an elevator is not working, it impacts the station access for the mobility impaired passengers, especially if only a single elevator is provided. We've often encountered discussion of, especially given the cost of building and maintaining elevators, where should we provide just one? Where do we need 2 escalators, or elevators rather? And increasingly, I'm seeing that we're providing dual elevators in a lot of cases, so that if one is out of service, the people who depend on them will still be able to reach their destination. Elevator capacity is calculated similar to transit vehicle capacity. That is, it's based on a standard area per passenger, simply divided into the floor area of the elevator. The capacity of an elevator then is dependent both on the size of the cabs, the interior size, and also on the cycle time of the round trip to do an entire cycle up and down, including whatever intermediate stops might be involved, and the time to load and unload passengers. And those can, of course, be affected by the selection of the equipment, the design of motors, and so forth to provide faster travel time than would increase the capacity, in addition to just shortening travel time directly. Station access elevators sometimes have doors on 2 sides for simultaneous loading and unloading. If you're dealing in a very high volume situation and really dependent on the elevators, doing the dual doors is a great idea. It really does increase the capacity because it reduces that loading and unloading time. I know quite a few elevators in the London system were built that way, and it works quite well. Moving walkways are an element found more typically in airports, but sometimes in our transit stations. The picture here is a transit station in Queens, New York. And New York City Transit has tried, I think, just a few of these. Typical speed is 100 feet per minute. Some of them, though, internationally at least, run up to 160 feet per minute, using methods to attain higher speeds. The capacity is essentially limited by the entrance and by stepping into the moving walkway. The speed of it is not a significant factor in its capacity for moving walkways. And the capacity has been found to be similar to escalators. Double width walkway has capacity of around 90 people per minute. That's a little more than a typical escalator, but pretty close. Doorways are a critical capacity element, and it's both a factor of the width of doorways and also the kind of door elements, whether they are free swinging, can swing in both directions. Revolving doors, as you see here, have some different capacity ranges, and we show ranges here because it really does depend quite a bit on the particular mechanics of the doorway system. I've encountered a particular design of doors in Montreal that they call butterfly doors. I'm not sure if anybody else is using this, but it's a single door that pivots and one side opens in and the other out at the same time. And those would pose a little different capacity than more traditional styles of doorways. They're actually using those related to a ventilation concern in the Montreal subway system. Fare control elements are critical. Again, I mentioned when I was showing the picture of the Portland Max station, and many of the light rail stations don't involve fare control, but many of our heavy rail systems do. And there are a variety of different types in terms of the type of opening, whether it's leaves that open or bars that turn in a traditional turnstile, and some other methods. And the particular style and configuration of each, and even the fare structure itself, can affect the amount of time that it takes people to go through turnstiles. So you see here another table taken from the manual, shows some rates that have been found through studies in various specific locations. The key there is really, if you're working in an existing system, then the best thing is to go do some local studies of people moving within your existing system. If you're designing a new one, perhaps to look at another system that has a fare control gates that are similar to what you're considering using, and preferably a similar fare structure as well. Ticket machines are typically provided in stations these days to automate the selling of tickets. Ticket machines are one of the least standardized portions of a riding transit from city to city. We see many different styles of ticket machines, some of them rather large, some smaller. Many systems have multiple kinds of machines, some that only take credit cards, others that take cash and credit cards, some that only sell monthly tickets, and so forth. So there's quite a bit of variety in those, and it's important to figure out the average amount of time that people will take so that you can adequately provide service to when you have a steady stream of people who are seeking to purchase tickets. A few factors in that, the surface time varies widely depending on the machine design. Infrequent passengers require more time because they have to figure out the fare system, figure out what they need to get where they're going, perhaps get used to handling either the credit card or the cash element of the machine. You should consider the impacts of out-of-service machines. Unfortunately, we all know these don't all work all the time, and you can count on some being out of service for some time. And then the question is there another one next to it that's likely to be working, or would people have to go further away to find one working? And if none was working, what would you do then? Also, some of the screens are hard to read in the sun, so you should consider issues of glare on machines that are outside, perhaps considering just an awning or a covering over the machine, or locating the machine under a roof or covering provided for other purposes so that it's easier to see through the glass screens. And finally, I'm going to talk a little bit here about microsimulation. As I noted at the outset, increasingly we've moved beyond the traditional spreadsheet-based level service types analyses to using methods that are computer-based microsimulation that, instead of looking essentially at averages of flows and averages of density, take the characteristics of individual passengers and model them through a system, through platforms, through all the elements of a station, sometimes also including outdoor areas, and then aggregate measures, and most of the same measures that are available with traditional analysis are also available through microsimulation, but it provides you some additional tools, both the visualization and additional ways to accumulate data that were not available by traditional means. The use of microsimulation is expanding significantly in the past 15 years or so. Microsimulation, which represents the cumulative movement of thousands of individuals, is better able to analyze and present the complex interactions of pedestrians in a busy multi-directional environment. What we really mean by that is that traditional methods are pretty good at analyzing a simple directional flow, say through a corridor, through a specific element like a stairway. But when you get into areas where there are lots of cross flows and interactions of both queues and people walking and people waiting, microsimulation really provides a level of analysis and visualization of those situations that was not really possible in traditional methods. And finally, the visual representations better communicate flow patterns and potential issues to decision makers and the public. My personal experience in conducting a lot of these, and we can generate lots of data, tables, and maps, but I've often found that what the decision makers want to look at really is the videos, and in looking at the videos, they can often see the problem. They don't really need the numbers per se. They can see the congestion, they can see where it's happening, and even pretty quickly tell why. Was it a turnstile or a stairway that's not large enough? It becomes visually obvious what's going on, and gives directly ideas about how to resolve an issue, either in an existing station or especially using that to analyze a future station or an alternative reconfiguration of a station. Okay, we've got a couple of images here of some of the outputs of microsimulation. As I said, you get video clips, you can have maps like the one shown here, and you can map different kinds of data. This is a map of mean pedestrian density, which essentially is a map of level of service. I don't have the legend here, but the blue is very low density, gray is areas where nobody even walked in this analysis, and green is a bit higher density. This represents a platform that is not overly congested at all. And each of those colors represents a range of density, and therefore also corresponds to a level of service from A to F. In this case, these are all A to C, I think. Some of the people who promote simulation software, and there are a number of different software out there, they will often highlight what their software can do in terms of the many different kinds of outputs, mapping, and so forth they can perform. But the key for us as people who are interested in designing transit stations, in identifying issues and resolving issues, is really to choose the parameters and the outputs from the software that really directly address the relevant issues for our project, and to pass essentially on ones that just add essentially fluff to a presentation, but don't really get at the issues directly. Now I'm going to ask Michael to switch us here. He's going to pull up some videos. Here they come. This is going to run for about 2.5 minutes, and we're going to see a series of different videos. These are all from microsimulation, all performed by Parsons Brinckerhoff. This first one represents at the top. The top area here is a platform. These are the subway cars. This is a subway line in New York City, new station that is currently under construction right now. This is the mezzanine directly above that platform. So you see people coming upstairs in escalators here. They appear at the top of that escalator here, then they're going to another one. The second model is also a station here in New York City. This one actually is Herald Square Station, the Broadway line crossing at an angle, 6th Avenue line over here. And this was a study for the now defunct ARC project, Access to the Region's Core, which would have had an entrance to its station over here. So we were studying the relationship and the impact of that new station on the existing station. This is the, as it says, the Arctic project in Anaheim, California. New multimodal terminal for Amtrak, eventually high-speed rail. It's a little dim here, but there are bus loading bays around the outside. Around the outside here are bus bays. We didn't show the buses in this model, but people are waiting for them there. And this again is a model for the Access the Region's core. This is 34th Street. My office actually is in this building right here. We were studying new transit entrances on some of the corners, studying the pedestrian flow across this very busy intersection, 34th Street, 35th. This is Macy's right here, the main flagship Macy's store. So we've used this. Although this is a street setting, it was part of a transit project because it was directly related to the effect of the transit on that setting. And the final video I have here is a stadium actually in Auckland, New Zealand. This is Eden Park Stadium. But in a sense, it was to study reconstruction of that stadium that happened before Rugby World Cup a couple of years ago. But it also is a transit project because there was a new bus terminal facility built here to serve people coming out of the stadium. And all the yellow dots here are all walking to a transit station that is just off the screen and out of the model here. Each of the other colors represents people going to a different mode as it was configured for that event. The blue were going to taxis, for instance. The purple are going to motor coaches that served, chartered motor coaches essentially, that served passengers. And that concludes the presentation. This just gives some information on where you can find some additional information. Of course, what I've been talking about is Chapter 10 on station capacity in the Transit Capacity Quality of Service Manual. As say, there's much more detail on all of this there, on specific measures, on exactly how to work through some of these calculations. Also refer you to John Fruin's original book. It has been published by Elevator World for some years. I'm not sure if it's currently in print, but copies are available in libraries and may be available from them still. And as you can see here, the Transit Capacity Quality Service Manual is available by some different means. You can order individual printed copies for free, and also PDF downloads on the TCRP online site. Also free PDF chapter download, so you can download the entire document, or you can download individual chapters on the web addresses shown. And also you can obtain individual or multiple copies from the TRB bookstore. And that's a final slide of those of us who contributed on the presentation. And I thank you for listening today.